Hi, my name is Vijay Kamble. I'm a graduate student from just recently graduated from Berkeley. I'm a postdoc at Stanford. So this is some of work that I did as a part of my thesis work at Berkeley. So the situation is the following: suppose you have n experts, and each of these experts are giving you recommendations every day about, say, stock investments, and you want to decide which expert to follow every day. The thing is that you don't know the quality of the experts. So some of them may be good, some of them may be bad, and you don't know a priori what it is. So basically, you want to design an algorithm that chooses which expert to follow every day, which minimizes regret. In the sense that, suppose there is one algorithm, there's one expert who is the best, in the sense that that expert is the one who incurs the least loss over time. So you want the algorithm's loss to not be much higher than this expert's loss. So for example, over here, consider this case of two experts and binary losses. So each day, expert one is incurring some loss, and expert 2 is incurring some loss. And here in the red circles are the losses incurred by the algorithm. These are the selections made by the algorithm. Okay. So you can compute the loss of each of these experts, you can compute the loss of the algorithm, and the additional loss that the algorithm incurs over loss of each expert is termed as a regret with respect to that expert of the algorithm. So you have this vector of regrets with respect to each of the experts incurred by the algorithm, and you want to minimize this vector component-wise simultaneously in an expected sense. So you have an algorithm which is randomized, and you want to do this in an expected sense. Okay. So this is an extremely well-known problem, combining expert advice, and there are a lot of things that are known about this problem. Say, for example, that if you have an n-step problem, then the regret grows like square root n, and there are several algorithms which achieve this regret. If it's a discounted problem, then the regret scales like 1 over square root 1 minus beta. And again, the same algorithms work in this case as well, which hit the optimal rate of growth of regret. But what is not known is what's the actual optimal algorithm. So for a fixed beta or a fixed n, what's the optimal algorithm which hits the optimal regret? And so the punchline is that we have a giant hammer which essentially solves this problem for any beta, for any discount factor beta. So the result is of the following sense. So if you give me an epsilon, I'll give you an epsilon optimal algorithm. Okay. So the main technique that is used here is the dynamic programming approach. So essentially, assume that, so consider an n-step problem, and suppose that you have somehow computed this set of all possible guarantees that you can achieve in n steps. Which means that for any point in this set, you have an algorithm which guarantees that the regrets relative to all the experts is no larger than this point. So consider this set of all points. And now the thing is, if we are able to, so the question is, what is wn plus 1? And if you are able to relate wn plus 1 with wn, then we can recursively compute wn, and our problem will be solved, right? And so if you think about it, what's going on is that, consider you have an n plus 1 stage problem. You can decompose it into the first step and the remaining n steps. And if you think about what's a policy in this n plus 1 step problem for a decision maker, it's that the decision maker first chooses a randomization over the experts in the first step. And depending on what losses were realized in the first step, the decision maker chooses a different policy to follow from step 2 onwards in the remaining n steps. But since we know what exactly can be achieved in n steps, this amounts to having a policy where you have a randomization over expert in the first step and a response plan which maps the losses that you see to a point in the set wn, which you already computed. Okay? So if you fix a policy, which is if you fix a randomization and fix a mapping, then you get a point in wn plus 1. And if you vary all the policies, all the randomizations and the mappings, then you get the entire set wn plus 1. And so you have a dynamic programming operator which maps this set wn to wn plus 1. And actually, the thing is that you're not really interested in the entire set wn. You're only interested in this lower Pareto frontier, because all the other points are suboptimal. And so you have an equivalent dynamic programming operator which takes in the lower Pareto frontier of the set of regret guarantees you can achieve in n steps and gives you a lower Pareto frontier of the set of regret guarantees that you can achieve in n plus 1 steps. And you can actually compute this operator. And what you can show is that if you take the sequence of lower Pareto frontiers by considering sequence of n-step gains, then this sequence of lower Pareto frontiers converges if the payoffs are discounted to a limiting set, and the limiting set is a fixed point of this dynamic programming operator, set value dynamic programming operator. And you can actually compute this set, and you can actually approximate policies that achieve different points on that set. So that's the basic idea. And if you see, so here is a performance so here is considering the example of 2 experts and binary losses. So these are the lower Pareto frontiers of the regrets that you can achieve for different values of beta. Okay? And you can also achieve different points on it. So over here, what I've done is, for the case of 2 experts and binary losses, you compare the approximately algorithm that we have against the algorithm that is extremely popular. It's called the hedge, which achieves the optimal rate of growth of regret. You can see it performs much better. So essentially, we have this machinery which gives you an epsilon optimal algorithm for solving any regret problem in an exact sense. So for reference, this is a part of my thesis, which is uploaded online. Right, thank you.